For Modern Physics 1. The purpose of this lab is to compare the observed motion of a mass on a spring to a predicted model that we create in GlowScript. We also need to understand all the energy changes that happen in an object that oscillates on a spring. The two fundamental principles that we use are Newton's second law, that change of momentum over change in time equals the net force, and that energy is conserved with the energy principle. We use the modeled equations for kinetic energy, gravitational, and spring potential energy, as well as the velocity update and the position update formulas. For the main result of the lab, the potential gravitational and potential spring energy have opposite signs, where when one is positive, the other one is negative, and the total energy remains constant in the entire experiment. For the experimental and model data comparison, the x portion is nearly identical to the y, the x portion is nearly identical to the modeled equation, and the y position data from the experimental data is a little bit more shallow in its minima, so it's not as identical. For the lab setup, we assume the spring, the mass, and the earth are all within the same system, so work is 0. The mass of the ball, LO, and the spring constant K are all found from the pre-lecture video number 52, and the ball and starting velocity, the ball position, and the starting velocity of the ball are both found from the first position we see from data and tracker, and the first two averaged together to find a velocity. The possible sources of error is some errors with tracker, with the video frames not loading correctly, and possible losses of energy in the experimental data, maybe possibly to thermal energy. For the code, as I said earlier, ball position and ball velocity are used from the first calculated points and the first point, respectively. The spring constant is considered when you use the equation that the oscillation period equals to 2 pi times the square root of mass over spring constant, and you solve for the spring constant. LO is also considered LO is also found when you consider the system in equilibrium, as shown in pre-lecture video number 52, where the spring force equals the gravitational force when you solve for LO, because that's the same spring. The energies come from the models that I talked about earlier, and the total energy is just those added together. F grav and F spring also come from the equations for gravity and the spring equation that I discussed. And the ball.vel and ball.position are update formulas. The interchanges that we see in the while loop later in the while loop also come from the same equations that I discussed just as previous slide, and the total energy comes from, again, those added together, and the definition that change equals final minus initial. So for the results, as we can see, the x position experimental and model and the y position experimental model are a little bit different, with x position being more accurate, but I think this can be attributed to the fact that tracker was not loading correctly for the first several frames, so that this may have affected the y position a little bit more than the x position and messed up the data. The energy principle is satisfied because the total energy stays constant, as I showed in this graph right here the whole time, the orange line, which makes sense because the work is 0 if you consider that all of the system includes everything that we include in the GlowScript. When I use two data points at the beginning, at the end of an oscillation period in the same position, they get the same period of 1.519 seconds per oscillation, which makes sense because it's the same spring with identical initial conditions, so the oscillation period should be the same. Thank you.